Okay, good morning, ladies and gentlemen, and welcome into your ME 491 Senior Design Seminar. Couple of announcements for the class really quick before we get started with the seminar today. Make sure that you're aware of your either interim design report if you're continuing to 492, or your final design report if you're ending with 491 is going to be due to me Monday of week 11. That's the 22nd of February. PDF to my email inbox by the end of the day. Okay, so hopefully you're working with your advisors on that final design report and kind of formulating that report. Also, you'll have an oral presentation, which will take place the Friday of finals week. So that's February 26th. We're sort of finalizing the schedule right now. I've kind of asked for your conflicts. So please, if you do have a conflict, let me know about that by basically the end of today. The final schedule is going to come out. So make sure you let me know about any conflicts that you might have on the 26th before the end of the day. So you can look forward to that too. You should be having conversations with your advisors about that at this point. Hopefully you've already had those conversations, but if not, what are you doing? Get to it. All right. Now, today we have a very special guest with our seminar today, and I'll just maybe give a little overview on the seminar today, and then I'll introduce our speakers. So today's seminar is a little bit different. I like to think about this as, some of you will go out into the world, and when you're working as engineers, you'll oftentimes have parts that are sort of like sent out for manufacture. And maybe you'll make an engineering drawing or of some, metal part or plastic part or whatever. And I would sort of consider this kind of like the engineering side of the equation, right? You're sitting at a desk, you're, making some engineering drawing, and you're designing a part that's going to be, hopefully, you think, built out in the real world and manufactured. And, the best engineers, when they sit down and they think about solutions to their problems and they're making their drawings or they're designing in CAD or whatever, have a very strong understanding of like all the modern manufacturing practices and technologies that exist. And I think, there's a lot of niche productions out there that unless you actually talk to experts in the field of manufacturing, you might not know about. And over the past couple of months, we've heard a lot of, engineering experts come in these seminars. We've had Tony from General Motors come in. We've had Jeff Krull, who runs a design engineering firm in Madison. We've had Kyle from Milwaukee Tool come in and give a talk. But today I want to sort of bring in some of my longtime friends who are on the manufacturing side of things, and I think have a lot of important messages, which I want to sort of drive home here as well, since I have the power of the pen or the mic in this situation. So let me introduce a couple of my long-term friends here. And I think Tyler might be away today, dealing with some real estate issues, but I guess I'll introduce Adam here. So Adam's been working in a specialized plastic manufacturing industry known as thermoforming for quite some time now. Adam's a bit more on the sales side, and Tyler's a bit more on the engineering side. But I think, Adam's message here is going to be the more powerful one, I think anyway. And the reason I bring these guys in here today is a couple of reasons. One, I think the manufacturing they're doing is really interesting, first of all. Like thermoforming is a really interesting process, and you can make some really interesting things. And I think just to hear about that process and learn about that is good for you guys generally as engineers to know about. And the second, and I think more important reason why I want to have Adam come talk today is he's got a lot of stories about interactions between him as a manufacturer and engineers that he's worked with in the past, and the importance of the communications between them if they're going to make certain parts. So I guess without further ado, maybe I'll just say that, introduce my friend here, Mr. Adam Bergauer. He's a general manager. I think, is that the appropriate title, Adam? General manager?
Yeah, general manager slash owner. Yeah.
Owner, sales expert, etc.
Yeah. Well, thank you.
With Global Thermoforming, they have multiple offices across the country and do a lot of this manufacturing. So he's going to introduce thermoforming, talk about some of his case studies, and I'll just say, Adam, the floor is yours. Go ahead and take it away.
Sounds good. Well, thank you very much. Oh, yeah, we'll get into that. So you want me to share my screen now?
Yeah, I think that's probably good.
Yeah. First of all, thanks for having me. I appreciate it. And hello, everyone. I don't think I can talk to everyone, so it's a little strange for me. I like talking to people, and I like seeing people's faces. But without further ado, let me share my screen and a PowerPoint with you.
I'll just say to the students, too, if you have questions for Adam as he goes, you can use the chat feature, and I'll relay the questions.
Perfect. All right, Kevin, can you confirm you can see?
Yeah, I can see the screen. Yep, looks good.
Perfect. Okay, so thermoforming is basically the process of taking a flat sheet and melting it in an oven and getting to a point of around 350 to 400 degrees or so, and then you form it over top of a mold. It's a lot more complicated than that, but that's the gist of it. The first slide I have here is real world versus 3D CAD. Engineers are, in my opinion, the person I want to deal with over, like, say, a buyer or anyone like that. But what like Kevin said earlier, what's very important for me, and not only for us to make our parts, but for the engineers to understand, is that thermoforming is not a perfect science. Unlike injection molding is the tooling process where you can control both sides, and then it's almost like a liquid injected into a tool. Thermoforming is more of one sheet that you can only control one side. Typically, we call that the Class A surface, which is the tool surface. So engineers need to understand that, when you put tolerances on prints and stuff like that, you can only control, like, for example, this part that you see here on the right side of the screen. That part, the front of that is the tool side, so it's a Class A surface. That's the surface that we can control. And in the next slide, I'll show you a picture of the tooling and an example of that. So yeah, typically what nominal thickness is called out. So if somebody calls out like a 3 millimeter nominal thickness, depending on the draw ratio, typically we start with like a 4 millimeter, 4.5 millimeter, so that when you're done forming, say like a 5-inch stretch, it'll be 100 or 3 millimeter up at the top, or at the worst case scenario, it'll be 3 millimeter. So yeah, I'll go into female versus male tooling. Female is obviously convex, male the other way around, or sorry, concave. And yeah, and then we have some secondary processes that we do as well. We do 5-axis CNC trimming. We do a lot of assembly, and we also paint. So yeah, so our next slide. So this is an example here of female tooling on the left side of the screen. This is a fully cast aluminum tool that we then fully machine back. So you can see there's some really tight radii in here, which our customer really wants. This is what we call a 2-cavity tool. So this is basically this right here. It's just flipped upside down. And we do this on parts where any parts are like over 1,000 or so that we have to produce. Otherwise, we would just make a 1-cavity tool. You basically just make the same parts double as fast. And then in the middle of the screen, there's an example of one style of this kind of part. And then on the right side is a CNC fixture. So with aluminum, you have to build in, with plastic, sorry, you have to build in what we call shrink. And this material is a material called Kydex, made by Sekisui. They're one of the biggest plastic providers in the world. And it's a fire-rated material, so that's why it's pretty high-dollar stuff. So yeah, from the mold on the left, we'll form the parts, and then we have to wait a day or so to let them shrink. And then they go on the fixture there on the right side. And then there's pretty cool 5-axis cutting. You can see on this last slide. So we do quite a bit of assembly on the other side of this part, and then we obviously do a lot of paint and then some decals and stuff like that.
Right. Can you just explain like the thermoforming process again really quick, basically sort of what it entails and how you might do it with this particular mold?
Yeah, so typically what would happen here is a sheet of plastic will be made, usually about 1.5 inches bigger than the mold all the way around. So that sheet is then laid into a clamp frame, and then the clamp frames are then sent into an oven, and then the sheet is heated up evenly. Kydex usually forms around 380 degrees, so you have to heat it up very evenly all the way around the sheet. This sheet, I believe, is 47 by 29, 47 inches long by 29, so it's nothing too big. We can form all the way up to 7 feet by 11 feet, by almost 5 feet tall. So like if you think about spas and tubs and stuff like that, we do stuff like that as well. And then later on in the process, or in this slide, I've got a big jet ski hull that we made. That's pretty cool too. But yeah, so that's the gist. It's then sent into the oven, and when it's heated to the right temperature, it's brought back over the mold. And then the mold goes up into the clamp frames. And once you create a seal around the edge, vacuum is then kicked on. And then if you have a good seal, the vacuum will then pull the plastic all the way down. I've got a couple videos, but I'm not sure if they'll play well. They might be really loud. We can try that if we have some time later, though.
Yeah, that's okay.
Um,
The basic idea is you take this piece of plastic, you heat it up, form it over the mold, and basically suck it to the mold surface. That's really, I guess, all you really need to
yeah,
know at this
that's
point.
right. Yep.
Okay, cool.
And then, yeah, so Kevin wanted me to go into like communication and some of the communication I've had over the years with engineers. I've been the GM now for around 15 years. So I've been doing this for a little while. And every engineer is different, but they're all very similar in certain ways. Kevin, I think, is one of the few engineers that I've worked with over the years that has pretty good, in my opinion, pretty good communication skills. There are a lot of engineers out there that they can communicate very well with the computer, but that's about it. And those people are very hard to work with. So I guess one thing I would stress is work on obviously on your engineering skills, but also keep in mind that communication is very important. And the people you're going to have to be working with, the better your communication skills, I'm telling you, the better off you're going to be working as an engineer, and the higher and higher you'll go. There's a new customer that we have out here called Nikola Motor. They're making electric semis. I'm not sure if you guys have heard of them or not, but they're basically competing with Tesla and who's going to make the first electric semi and bring it to market. So those are some of the big parts that we form out here. So yeah, I prefer working with engineers over buyers because, as I told Kevin, engineers don't always care about price, which is something I care about, but they're more concerned about making sure that that obviously all working parts mate together. And that's what you have to understand in thermoforming is that you can only control one side. So when you have mating parts, you have to build the tooling around that. So if you got a male part, you can control the inside of the part. Female part, you control the outside of the part. So it really just depends on, what you're working with. And every situation is different. Um, yeah, I think, and then, when designing new products, it's always best to have the manufacturer in that communication before you take it to production, because we'll see stuff like draft angle, stuff like that. If you have undercuts, it just saves a lot of time. So we prefer working with our customers, and once our customers get to know us, they prefer that as well too, because then we're all working together and we all have more eyes on that specific drawing and or part. So yeah, so that's head for that. So here I've got on our website, I updated our website about a year and a half or so ago, and we do a blog once a month. So if you guys ever are interested, let's see. So thermoforming versus injection molding. I basically built this blog to kind of show people the process and to show like from start to finish what you can expect. So in thermoforming, the tooling is a single 3D form, right? In injection molding, it's double-sided. So it's basically two things put together, and then you inject plastic. Forgive me if you guys know this. I'm just trying to help. And then the molds then come apart, and then the part spits out. In thermoforming, it's just one male or female tool that you form over, and then it's then brought off of. So this gives you a good idea of what we can do and then what you can expect. There's an idea of the tooling. This is considered a male here.
That picture is really quite nice. I think that really drives home the idea.
Exactly. Yeah. So that's an example of male tooling. The thermoplastic sheet in here. These are the clamp frames. This is the tool. So as soon as it gets a seal, like I said out here, the vacuum is then kicked on and then it pulls down the rest of the way. So here's the cost difference. Tooling costs, obviously, with us, we can make tools a hell of a lot cheaper. Whereas with injection molding, it's very, very expensive. But then their part piece, so if you've got the quantities, like anywhere over 10, 15, 20,000 is generally where you're going to want to go into injection molding, because your ROI, your return on investment, is going to then pay off sooner. So here's an example of that. So anything up 500, 1500, 2500, that's the niche for thermoforming if it's like a big part. Once you get over that 3,500, 4,500 pieces, then you might want to look into injection molding. It really depends though. I mean, every single part is different. But this is based on a 4 foot by 5 foot part, which is a very expensive tool for injection molding. Then here's an idea of the lead time. And this is from start to finish. So like we can make tools in as little as a week or two, but I typically tell people that that first week or two is basically nailing down the design, and then it goes into me quoting it, and then it goes into ordering the materials that are necessary to make the tool and to make the plastic, and then we got to get you in the production schedule. So typically from start to finish, it's anywhere from 12 to 14 weeks in thermoforming, and in injection molding, it's around 18 to 24. So it's quite a bit longer process. Here's some other considerations here. So this right here is what I was talking about earlier. Does it allow for different thicknesses within a single part? It's limited in thermoforming, but injection molding, you can do that. They both paint pretty well. And typically you don't go above a 4 foot by 4 foot injection molded part, because then the tooling just gets outrageous. So that's a good example of thermoforming versus injection molding. Here's an example of one of our machines here. It doesn't look that big, but that machine's about 40 feet in diameter, so it's pretty big. And it forms up to 7 by 11 feet. So yeah, that's awesome. So that's thermoforming versus injection molding. And then here's an example of a part that we just made. This is for one of the first jet ski hulls out there that's going to be thermoformed. Typically, all of them are made by fiberglass, but in the last like 5 years or so, they've gotten a hell of a lot stronger thermoplastics. So this is a polycarbonate filled ABS with a polycarbonate cap on it, and it's also got glass filled in there as well. So it makes it hard for me on my side to form it, but it's very, very strong once you get it formed. So that's an example of one of our 5-axis CNC routers. It cuts up to 6 by 11 feet. This part's 11 feet tall. It's pretty big. It's one of the bigger parts that we form. And that's for that same customer. It's called Nikola.
Those of you that took my composites class, you know all about increased strengths of thermoplastics that have reinforcement in them. You know all about that. Okay. Keep going.
Yeah, it's a good theory, right? But forming it is another thing, like on our side. So that's another example of making, something very strong. When you put a lot of glass inside of a plastic, it makes it not heat evenly, and it's a lot more challenging for us. But it is a lot stronger, that's for sure. That sheet weighs 135 pounds, so it was very hard to move that thing around. So then I've got one more, thermoforming versus fiberglass. Same example here. Well, not same example. It's thermoforming versus fiberglass, right? Thermoforming, fiberglass is obviously, so what we've done over the last 5 to 10 years is anything that is made from fiberglass, which we do a lot of these antenna things for 5G, which is questionable whether or not people like that. But they used to be made out of fiberglass, and now we're thermoforming in them. Same thing with that jet ski hull. A lot of things that were fiberglass are turning into thermoforming because we can produce, like for example, that jet ski hull, we can make 150 to 200 of those easily in a day, whereas fiberglass, they might make 10 or 15. So it's just a heck of a lot faster process.
Yeah, in a day, man, you might be lucky to do a handful in a day.
Yeah. Exactly. And then fiberglass, thermoforming is 35% lighter than fiberglass. And then we can obviously put different colors and textures. You can do that with fiberglass, but you have to paint it because typically it's a very messy process. And thermoforming is recyclable, except for when you put glass in it and stuff like that. But I would say 85 to 90% of our plastics are recyclable. And then you can see down here, these are some of the strengths. Obviously, I don't list any of the weaknesses in thermoforming.
Because you're trying to sell to the world.
Right. So
but those weaknesses might include things like limitations on the thickness control,
right.
High volume production, super high volume production might be a problem.
Right.
Yeah. Cool. Interesting to know and understand those things.
Yeah. Yeah. So feel free to go to our website. It's just globalthermoforming.com. Kevin can send you guys a link. I've got some other blogs and stuff on here. Here's an example. So fiberglass generally is stronger, and it shows you right here that it is stronger.
Yeah.
But it's not as fast, and there's other weaknesses. But yeah, I've got like 10 or 12 different blogs on there too, guys, if you want to check them out.
Yeah, there's
And
one I
then
think that there's one section of the website I think is particularly interesting. I'm going to share my screen here really quick if you don't mind.
yeah,
Uh,
go ahead. Do I have to stop sharing?
no, no, I got it. So
Okay.
there's one section of the website here that actually shows some of the engineering drawings associated with some of these thermoformed pieces and parts. And so here, this is one section in the gallery of the website that shows a lot of that sort of stuff, which I think is kind of cool. They've done like kind of a cupcake holder here, which you sort of see this clamshell idea, and some of the engineering drawings that are sort of associated with that. I think that's kind of cool. Okay, I'll get you back now.
Yeah. Um, let's see here. Okay, you got me back?
Yes.
All right. So I just have, I think, one or two more slides, and that was about it.
Yeah.
Yeah, so then the quoting process. This is an example of one of my quotes on the right here. It was actually for that wave that I just showed you. We made 6 different parts for them. So I put a lot of money into our website, and some of you may or may not know what SEO is. It's basically when people type into Google thermoforming or plastics or stuff like that, our name hopefully pops up towards the top. And that has gotten us customers like Nikola. Tesla is now one of our customers. SpaceX is a customer of ours. So it really kind of shows. We're also ISO 9001, so that really helps, and it gives me a good sales tactic. Once I tell people we're ISO 9001, they're like, all right, we're good.
Yeah. Can you explain ISO 9001 as a quality control metric and like everything that entails? I think that's important.
Yeah, so it's going to be hard to explain it, but I'll try to give a brief overview. It's basically a quality management system for manufacturers. It gives you controls on like your quality, your repeatability, who are your vendors, who are your customers, and then also it basically gives you a good way to make sure that everything is checked and then double checked and then triple checked, which can be annoying because it means there's a lot of paper trail that goes with it. But I prefer that. I'd rather be a little annoying and make sure that we don't miss things.
Right.
And our customers really prefer it. Same with engineers. It basically gives them a really good idea that we know what we're doing and we're double checking and triple checking ourselves.
So what
Um,
sorts of things do you have to do to be ISO certified that you wouldn't normally have to do?
Yeah, so like quality sheets have to be out in the plant for every single job. And each part is different. So like some parts you'll check overall thickness, some you'll check distances and lengths and stuff like that. Some we make like a mobile X-ray unit that we have to check a lot of different things on. It also requires that we have material certificates called COCs,
Yep.
Certificate of Conformance. And I mean, there's a lot more to it. It basically has a paper trail for every moving item in our plant.
Right.
And then it also has a double check on it too to make sure that everything's being checked. So an example from start to finish, when we receive plastic, that plastic is both counted and checked to make sure that it's right, to make sure that the quantity is right, the texture is right, the color is right, basically everything. So we have one guy that's in our plant that does that all day.
Hmm.
And then from that point, it's then labeled with the customer, the part number, the right rev, making sure everything's on there.
Right.
Um, and then it'll go into our production schedule. And then
Yeah.
from there, it's then formed and then cut and then trimmed and assembled or painted, whatever.
So yeah, just
But
a lot of bookkeeping and quality control that might not otherwise be required.
correct. Yeah.
Right. So that
Uh,
might be important for the students to understand. Like if you're looking at getting a quote from some manufacturing company and maybe one's ISO certified and one's not ISO certified, one that is ISO certified, they have a lot of quality control metrics in place that, might be useful in the long run and help you track all of your information well. If you're getting a quote from them and, having parts made by them, it could be helpful.
correct. Yeah. Most people who, like I said earlier, when I say that we're ISO 9001 certified, it basically gives them confidence that we know what we're doing.
Mhm.
Which isn't always the case, but but yeah, it's yeah. So that's the gist. So you can see here. This is one of my quotes. So it usually comes in either through word of mouth, like they've done business with us before through somebody else, or an engineer then goes to like a new customer of ours, and then they call us. So keeping those communications and keeping those connections, you guys, is pretty important throughout your career, because it can always help you to have those connections there for you.
Cool.
Yeah, that's basically what I had.
Awesome. I do have some questions prepared for you.
Okay.
So maybe we can have a little Q&A now. There is one student here who's asking about the ISO certification. He's asking about how those standards are set. So how is ISO 9000 standardized, and what sorts of things are required of you from the ISO certification standpoint? I think he's kind of trying to make a point here that individual companies sort of establish their own ISO standards, and basically you just have to adhere to the standards that you yourself create. So is that really the case, or are there certain requirements that ISO forces on you that you didn't yourself enforce? You know what I'm saying?
It's actually a really good question, because he is right. He or she is right. But it's not that simple. There's something called a quality manual that you have to build your system off of, and we're also audited twice a year. So if we're not doing what we say we're supposed to do, they're going to catch us, and we're going to lose our certification.
Yeah.
So it is somewhat accurate, and some customers that I know of that are ISO certified, they basically do all the work in a week, right before they're audited. So it's really not even a point of being certified. But I typically use it. We use it every day here for quality, and just for records, just making sure that everything is watched. But it can get a little frustrating and a little tedious.
Yeah. Do you mind putting your camera on?
Yeah, I was trying to. It's not. There it goes. Yeah.
Ah, there he is. Okay, got him now. I'm gonna put the spotlight on you. All right, you're gonna get the spotlight.
Sounds good.
All right. So I just have a couple questions, and mostly kind of like pertaining to new engineers that might be working with you in general, and some things that they might do to help themselves work with you, right? So anyway, thermoforming is a bit of a niche manufacturing process, right? Like, not everyone coming out of engineering school is going to know about thermoforming, what it is, what it entails, the benefits, the drawbacks, etc. Not everyone's going to know about 3D printing, the benefits, the drawbacks. Not everyone's going to know about ceramic manufacturing, the benefits, the drawbacks, etc. And as I kind of like mentioned at the very beginning, I think the best engineers in the world are those that sort of understand these processes as much as they can to design the best part with all the ideas in mind of draft angle and what's the thickness you can require and what's the tolerance you can make on your thickness, and what side is class A and what side is not, all those sorts of ideas. What's happening? Why is something's happening here? Okay, I got it.
I'm not sure.
Sorry, you lost the spotlight, but I got you back. All right. So my question then is, do you have any suggestions for how an engineer that's not very familiar with thermoplastics or thermoforming in general, how they might go about uncovering what some of these niche manufacturing ideas are? And once they have, are you receptive to working with them and sort of teaching them the ropes, right? So that's generally the question. And do you feel that that is true for most manufacturers or not?
Yeah, I mean, a lot of these new companies that we're working with that are tech companies, like engineers, a lot of these engineers are just out of college. So I literally like teaching them. I prefer they learn from me rather than thinking they know what they're talking about when they've never worked with thermoforming.
Right.
Now, granted, I'm not nearly as smart as you guys are in engineering or the science behind it. But I've got 15, 20 years experience. If you listen and we work together, that is by far the most important thing. So like there's this new company called Atlas Motor Vehicles. They're out here in Arizona as well. They're making 2 electric trucks. One's a pickup truck and one's a flatbed. Their engineers, they all came over here. They've got quite a few people, 10 or 15 of them, along with their owner. And they all came over and they literally listened to everything I said. And then they designed based on that.
They came over to your shop to actually learn about the thermoforming process.
Correct. Mm-hmm.
Yeah.
Excellent. And I would highly recommend that. Like if you ever get opportunities to go visit your customers, if you're an engineer, go learn their process and ask them questions. They
Right.
typically, especially a sales guy, they want to talk to you. And they'd rather have you learn from them and put it into the drawing rather than have to teach you after.
Right. So I could see that being a particular problem is like sometimes ego gets in the way, right? Like I'm an engineer. I went through 4 years of highly trained mathematical education. I know what I'm doing. I'm going to design this mold and you're going to make it rar. Okay. Okay. That's silly, right? Like obviously I can hear the machines in the background. Okay. Like I know that you're making this and you know how to make this. And so it'd be egotistical for me as an engineer not to come to you and say, hey, tell me about some of the restrictions and limitations of your particular process so that when I make this drawing of this piece or this part that I want to make, I can make it properly and have the draft angles appropriately and have the thickness tolerances appropriate and all these sorts of things. I think that's really important. And you sound very receptive to this idea, and I think most manufacturers are also receptive to this idea. Is that what you experience in your history?
Yeah, you're 100% right. And I mean, sometimes people want things that are almost damn near impossible. And I just give them like a note, like in my quote, I'll say, based on our conversation, or I'll say something along the lines of, we're not guaranteeing it. We think we can do it, but we're not sure, because people do like pushing the boundaries, and I do too. It's just when nobody has done something before, you kind of have to just say, well, we can try it. But it's better to work together and to come together and meet in the middle and try to come up with a solution. Usually in thermoforming, you can always find a way to do it. You just have to think outside the box.
Yeah. I think a lot of it is communication as well. Engineers speak a certain language that's, what is this tolerance? What is this stress that it can handle? There's some vocabulary, vernacular that gets thrown around that sometimes can be difficult. And there might be this barrier between someone who's manufacturing and someone who's an engineer where you don't necessarily have the vocabulary to communicate properly. So I think that's also important to maybe communicate with the right vocabulary. And I don't want to say a dumbed down vocabulary, but you have to understand, I'm talking to the students here now, that you have a very specific education when it talks about stress and strain and some of the things you understand in material science classes like polymer chain mobility and all these sorts of things that you understand as engineers, but maybe that vocabulary is not ingrained in some of the manufacturers. And so sometimes those barriers can be difficult. I don't know if you have any specific examples of, trying to work with engineers in the past that it hasn't gone well because they communicate poorly or don't have the right vocabulary or don't explain things well. Do you have any case studies you might want to say in particular or not?
Um, so typically the guys that we have trouble with are the quality guys. Because quality guy or girl, because those are the ones that if it's on the print and it's not to that, even if it's off by 1,000, they'll ding you, and even when in the real world it really does not make a difference, they'll reject the part just because they want to.
Well, some of
Those are
that
the guys.
comes back to the engineer, doesn't it? Who specified that on the drawing.
Yeah, very true. But also it could be the salesman's fault, saying that they should have noted that. So as long as three people, all the teams work together, and they really, like I said in the beginning, it's real world versus CAD. CAD, it says one thing, right? It's got a nominal thickness of 100 all the way around. That's not possible. I mean, it is possible, but not in thermoforming. So when you've got different draft, you got a part that's that tall, you're going to be thicker up here, and it's going to be thinner down here. So you just have to work together and realize that the real world is different than CAD. But that has to be communicated though. So both by the thermoformer and the engineer and the buyer, all people have to know the details, and making sure that everybody knows that, if it calls out a certain dimension, you have to quote it based on, it's going to fall in this range, not it's going to be perfect.
Mm-hmm.
So just making sure that that's upfront and communicated is important.
Yeah. All right. Another student question here. I know this particular student, he works in the 3D printing facility here on campus, and he's interested in this. He's asking about the hull project for the jet ski. And specifically, he's asking, is there any prototyping process before actually going and making that full mold itself? Like, do you have like a 3D printing where you're 3D printing like a small scale mold to see how it's going to work before you actually go into the full mold production? Or do you just like, we're making this mold, rar, go for it? Like what's the idea there?
Yeah, so typically the science department is doing a lot of research on the exact thermoplastic, right? So Nikola has their own science department, right? So they had guys talking to me left and right and my suppliers because like I said earlier, I'm not a scientist. So I do not know thermoplastics science. I know thermoplastics as far as like what it is, what it's used for, that kind of stuff. So we were working with all the data sheets, the tech sheets, and I got them samples and stuff. So they did all that research on the side while me and the engineers were building the actual hull drawing. So they would constantly call me saying, what do you think about this? Where is it going to pull thin anywhere? Blah, blah, blah. And then we went to a prototype tool. So we didn't like make a small tool, like a 4-inch tool or something like that. We went straight into a prototype tool because they also, if you think about the business side, they've got investors, they want money, that kind of thing. So they're also being pressured on their side. So we went right into a prototype tool, which in that case, it was very difficult for us to form that because I should have been a little bit stronger on my side, saying that they need aluminum in certain areas. But when you talk about a part that big, that tool was like 25 grand, even for a prototype tool. For a production tool, it's like 50 grand. So there's a huge difference in price. And yeah, so it was just very, very difficult to form because typically in thermoforming, you have to heat the mold up, especially when you're using polycarbonate. You have to heat the mold up to like 180, 200 degrees. I was forming on a soft tool, and you can't heat a soft tool.
Yeah.
So it was a material called Ren Shape. It's like a polyurethane cast material that's really easy to machine, and it's really good for prototyping, except for when you're using polycarbonate ABS. It was very difficult.
Right, because that material will start to soften and deform at temperatures required to mold polycarbonate.
Right. And yeah, so we had to heat that up to about 440, 450. So when you've got that hot of a plastic going against a soft tool and it's not aluminum, it'll tend to rip it as well. So you've got a shrink rate for every single plastic, and you have to let the part chill at least down to 180 degrees or so. So you're going from 450 to 180. It's got to sit on there for like 5, 6, 7 minutes. And when that mold came down, the part, you should have heard the cracking that it was making because it was trying to shrink on the mold. Every shot, we ran about 30, 35 shots on there. The mold is surprisingly still in shape, but it's cracked all around the outside because of the part. It had that lip on the outside that it was trying to pull every single time.
Yeah, we talk a lot about in their engineering curriculum about shrinking of metals, thermoplastics, etc. The larger the part, the more shrinkage generally you're going to get, just because it's shrinking uniformly over the width, and so especially larger parts, that's a bit of a problem. So interesting. So yes, to answer your question, Kyle, there is some prototyping, and prototyping can sometimes be difficult because you're trying to make a cheaper tool, but that might not be the best for actually evaluating whether or not it's a good prototype. So it's difficult balance there, right? So interesting.
Yeah.
Okay, a couple more student questions here. One from Mo here. Do you have engineers unfamiliar with thermoforming reach out to you that just simply want to learn about the process and if it's viable for their design solution?
Yes. Typically, if they're not a customer, though, it can tend to use my time. So, like, if it's a friend or something like that, I'll do it outside of work or
me.
in work. Yeah, like you, obviously. So I actually have an ISO audit here in a little bit, so that's fun. But yeah, I mean, I will talk to people, but typically, most people that call me are potential customers.
Mm-hmm. Right. So you have to invest a little bit of your time on the front end, but you don't want to feel like you're getting taken advantage of.
Correct, because I could literally talk for days. Yeah.
Yeah. So another question here is, are there any sort of cutting edge technologies in thermoforming that you're looking at right now? And what would some of those be?
Yeah, there are new machine options and accessories on. I just bought a new machine last year. I'm buying another one in a month or so. And there's something called pressure forming, which is not new, but it's a process that's getting better and better, which gives you more detail on parts. So instead of just vacuum, you're using a box on top as well that pushes really, really strong air, and it helps you get all the detail that's in the tooling.
Right. So not just pulling the vacuum pressure from below, but also applying positive pressure from above.
Correct. Yep.
Right.
It also gives you better material thickness control because it spreads out more evenly. There's something called twin sheet thermoforming, where you actually have a bottom sheet and a top sheet, and then it's formed together. And it creates stuff like pallets, twin sheet pallets, stuff like that. That's not necessarily new. Some of the new things I see are on the machines. They've got new sensors on the machines that literally you tell what the sensor to read as far as a gauge goes, and then it'll come out when that's read, that temperature. And you can put multiples over there of that on the machine. So right now, this new one that I have 6 sensors, one in each 6 zone location.
Yeah.
That's pretty cool. It really helps with like setup times on new parts. So you basically tell, all right, I want the plastic to be 385. And then as soon as it hits 385, it comes out and forms over the tool. There's actuated molds, which are features like if you have undercuts, that the molds will actually actuate back out with air. So that's pretty cool. For the most part, those are about the things I'm seeing lately. I am waiting for new stuff. There's that Gibson guitar case, Kevin, that we made, where we layered thermoplastic. We layered an ABS, like a 1/16 of an inch ABS, half-inch piece of foam, and then a 4-way stretch velvet. And then I put heat-activated adhesive in between all layers. So you got one big sheet, and then you went to go heat it up, and then you form it over the mold. So that was a pretty cool.
So you're forming like a laminated structure all in one go, yes?
Yeah, and then the heat activated, cool. Yeah, it keeps it together. So that was a pretty new one. I created that about 5 years ago. So yeah, that's pretty much for the most part what I'm seeing.
Yeah, that's awesome. Another question here, and then we'll get you to your audit, which sounds as exciting as the dentist. So Ethan asks about kind of the strength of plastics as a limitation. So he says it seems like limiting factor in non-composite thermoforming, so this is just pure polymer material, is sort of the strength of the plastic. So he says, do you think purely plastic materials have potentially to be used in higher strength application, or do you think you're always kind of having to make a concession for reinforcement if you can't meet the requirements? Because there's limitations on thickness that you can have, and so if you have a lot of load on your piece, it can only be so thick before you have to start to go to like reinforcement to buff up its strength. So is that is that a concession that you make? What goes into those sorts of decisions?
So with every plastic we use, there's something called tensile strength that you guys probably know well.
They know that.
So and that he's right. So with any thermoplastic that is not formed, that the properties change after it's formed. And not only that, but like you said, things will thin out in certain areas. So in thermoforming, if you are going to need reinforcement, I recommend it every single time. Like that hull that we made, they put an inch layer of reinforcement on the inside. Then they also put fiberglass on the inside. So they reinforced the heck out of that thing. And unfortunately, the way it is right now, thermoplastics, they're not as strong as fiberglass yet. Now they're getting there. They're getting closer. But like exactly why we're doing the hull right now. But if you need like a hull, or it's basically based on whatever strength you need, and then you take that strength in any square inch, and then you just test it and see if it'll pass those tests. And if it's strong enough without the reinforcement, then go ahead. If it's not, then you're gonna have to reinforce it.
Yeah. So there is some back and forth here, I think. And Ethan, your question is good. Is that you as an engineer are concerned with the strength and how much it can bear, and Adam's got this limitation on what he can actually manufacture. So maybe you need to make it a certain thickness as an engineer, but Adam can't make it to that specification. So again, that's where this communication comes in and is important, and that you have to have this sort of back and forth. Last comment we have from a student here. He says, "Office dog, nice." So they got some office dogs roaming around in there, and I don't know if that's part of the ISO audit, but
yeah, they're required as far as the ISO goes.
Yeah, sure.
For mental.
All right. Well, that's 10:45 our time, so that's probably going to be it for the seminar. Really appreciate you doing it, man. It's really cool to see sort of the other side, the manufacturing side, and I think important messages here being that communicate with the manufacturers often, especially if you're just like sending some part out for manufacture. You got to make sure that they can make it well and repeatable and have communications with them. So
that you said here, lose your ego. Just let it go. Just try to work together and communicate together.
Yeah, exactly. It does take some admitting that you don't know all the details, to and that's, hard to be vulnerable and say, I don't understand everything. Can you walk me through this? And I think especially as a young engineer, the more you're willing to do that, the more your knowledge will grow and you'll just be a better and better engineer in the future. So that's cool. Any last tidbits of knowledge for these
No,
students?
just try to get a good grasp of cost as well if you can. That's where your buyer. Every company works different. Some engineers work directly for the buyers. Some engineers are completely separate. So yeah, just keep your communication open, and yeah, I think that's the biggest thing for me. The engineers that we work with that communicate well, they always end up with a good product at the end of the day.
Yeah.
The other ones are tricky, and they're always going to be tough.
Suspicious. Yeah.
Yeah.
All right. Well, appreciate it, man. We'll let you go now. Thanks again for doing it. Okay.
Yeah. Good luck, everyone. That's it.
Yep. Bye-bye.